A chance, we're going to talk about fault tolerance. How we can make a system that tolerates fault to not make failure. So we can see that a little bit in terms of probability points. So last class you learned how to count. Of course, you know how to count, but sometimes this counting gets complex because it's not limited. Talk about sampling. So when you have a bunch of items to select, to sample, trial, how we can do that. Sometimes we are doing sampling with replacement, sometimes without replacement. Last class we talked about without replacement. When we take it, we don't return it back. Today we're going to talk about when we return it back, what's going to happen. So without replacement, last class, we said sometimes order matters. So when you're playing card, sometimes you care if the first card be king or like ace, for example. It depends. You know, it depends the type of game, of course. I don't know what you're talking about. But most of the time, order matters. In that, in some other applications as well. Sometimes order matters, sometimes not. If the order matters, the counting become more. Because different order consider sequences. In the case that order matters, we said we can count the number of outcomes using permutation formula. So the permutation formula went something like that. Remember, I want to remind you. So we said replacement. Last class we talked about without replacement. And we said when we don't return it back, still two situations can happen. Order matter or order does not matter. If the order matters, we count the number of outcomes with this formula. Remember? N factorial, n minus k factorial. We call that permutation. If the order doesn't matter, we are using combination formula. The notation is like that. Because if order doesn't matter, we need to shrink the number of outcomes. So we shrink them with the same case coming in here. Okay, n minus k. So the example that we mentioned, for example, if you are playing cards and you are drawing 5 cards from a full deck like 52. So first you have 52 case, you are taking 5, remember? And then when the second time you have 51, because you already take 1 off, and then 50, and then 49, and then 48. All possible cases that can happen is multiplication of them that come from the permutation formula. But if the order is not matter, in this case, so you need to divide it by k factor here. So this k factor here actually consider some cases, eliminate. Okay? So we explained this part last class. Today we want to talk about with replacement. So imagine in that playing card, you're taking 5, but return them back. When you look at them, okay, it's a king. Return it back, so you have more chance to take it again. Another chance to take it again. So in that case, we call that with replacement. This was last class. Call it A, for example, and B with replacement. This is something that we want to talk today. In replacement, when we have replacement, order matters. Sometimes order not matters as well, doesn't matter as well, but it's not happened that much. We mostly cover the first part, but I can explain the second part of order matters. Okay? So in the example of card, you have a full deck, 52. So you take 1. So you have 52 cards. They are different. So you have 52 choice. Because it's return it back, you again have 52. Again you have 52 because you are doing 5 times. The this is 252. 52. This is equal to 52 over 5. Okay? So this is how we are counting the number of outcomes when we return it back. When we replace it back. But this is very simple, not complicated. But sometimes we can add some actually extra conditions. We call that actually some extra information. So, for example, you want to see in this example of the drawing card is a little complex. But what about you have a jar of marble? Okay, the jar is a little deformed. So you have some green marble here and some red marble. There are lots of marble here. And you are taking, for example, 10 of them out. Okay? You don't know how many marble is inside that, but you know you are taking 10 of them out. Okay? What about we are counting number of outcomes? If we know, if we want, for example, we take 10 out. Okay, we know that. What if we want 2 green, and 3 red. We're going to make it a little complex. We give more constraint in this case. Now, if we know these two, we take 10 of this out. What if we want 2 green and 3 red? So in that case, how many, situation we're going to have? For example, we can have color. For example, green, red. It can different, order matters as well. And like that, it can be green, red, and so forth. So we want to see how many cases we can have if we have these conditions. So this is something that we had before with actually combination. This is still combination. We are kind of taking, two from, this is kind of combination. So we're going to see these cases as well. This was for 2 outcomes when it was just red and green. What about if we have more than 2? That makes it a little complex, and we're going to see that today. Okay, let's get started. I just wanted to see what we want to talk about today and how we can connect it to the last class. Last class we did some actually sampling. We are going to go still in sampling, and we're going to add these extra conditions to our sampling as well. But still we are in counting. Counting is kind of important because it's part of probability. When we want to find probability, we always need to know how many we have that we want to actually find probability. So the number of outcomes, the overall number of outcomes is always important in probability. Okay, so let's see what we have. Sampling with replacement. So sampling with replacement means replace the object. Okay, so you choose it, you see what is that, replace it back. And so selection is followed by a replacement. So as I said, so it's not changing the collection. It's not changing the collection. So if it was, for example, a full deck of cards, still going to be the full deck, 52. They're not changing that. So it kind of makes it simpler. So if we just do one time, is one trial. When we do multiple time, is multiple trials. Sometimes we call it a sub-experiments. And so sample space is not changing. For example, if we do 5 cards from full deck. So what we're going to have, if we do just one, we have 52 if we just do one trial. If we do 5 trials, we're going to have 52, 52, 52, 52. 52 over 5. Makes sense because you're 5. So, and order matters. Order matters, so this is something that we need to know. Let's see one example. This is a very famous example, we always use it. When, for computer, you have multiple USB, but you can connect different different things, different camera, printer, memory card, whatever. You can connect different parts to your USB slot in your computer. So, but you have just two. So you have two USB slots. And for each one, you can connect, for example, memory card, you can connect camera, and you can connect printer. So you have three different choices that you can connect to that. But you also can connect both of these to one. Like, for example, you can have camera here and camera here too. So this is allowed. But if you put memory to one and camera to the other one, this is not equal to camera to first and memory to the second. That's different. Okay, so the order matters. So I want to see how we can describe that. So the order matters. That's the main point. Replacement. What about replacement? I just explained it. When you have C and C or M and N, you can replace it. So replacement matters too. So replacement is okay because we have these cases. You can connect both of, USBs to same printer or same camera or whatever. Okay? So in this case, we want to find number of outcomes. What is the number of outcomes? So we like this. The number of outcomes is, you have three choices for the first, three choices for the second, so it's going to be 3 power 2. 9. So if you want to write it up, you can see that, like for example, you can do memory and memory, memory and camera, memory and printer, and camera and memory, camera, 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 printer, printer, memory, and printer, camera, and printer, printer. Yeah. All the cases that you can have. Okay, so this was something simple that we can count it, we can write it up, but sometimes it's hard to write all the sequences. So we need to find a formula. But you can guess the formula from here, but in the next slide I can write up the formula, the mathematical formula. Any question about this? So that wasn't difficult because it's kind of similar, but understanding that replacement is okay is a little tricky, because replacement is okay because you can have this case. Clean this up. So we're going to have 3 over, so the 9 possible cases. So the formula coming from here, the counting rule. If each trial has n possible outcome, so n possible outcome, like for example, for example of USB, m is 3. You have 3 cases for it. You can use camera, you can use a memory or a printer, for example. And the trial is repeated n times. So we are repeated n times. We have here two of those. So in this case, the total number of outcome, sometimes we use S, sometimes we use this thing, is m power n. So M is possible outcomes, and N is number of repeating. Okay, so that's coming from that. So the theorem, so it means we have n power n ways to choose this replacement. So that's something simple. So example, this can happen for binary numbers as well. You probably had some, I don't know, digital logic or something that you know about binary numbers. Binary numbers, you can use 0 and 1. We have a binary number that has 10. The length is 10, so this is 10. Okay, so this is 10, and each one can be 0 and 1. So then, actually, sample space is 0 and 1. Okay, so we have 10, and each of these can have 2. So what we are asking, how many outcomes we can have. So in digital logic or digital systems, we know that, for example, if we have 2 bits, we can have 4 different cases. With 2 bits, we can have 0, 0, 0, 1, 1, 0, 1, 1. Okay? If we have, so it's 4. That is 2 power 2. If we have 3 bits, we can have 0, 0, 0, 0, 1, 0, 1, 0, and so on. It's going to be 2 power 3 means 8. If it's 10, 2 power 10. So 2 power 10 coming from this formula. So let's clean this up. Because each of these can have 2, because 0 and 1. So M is 2, and N is 10. So the number of outcomes, or S for the matter, is equal to 2 power 10. Okay, you had that before, of course. Because it's binary numbers, it's so simple, just 2 cases. So it's easy to figure it out. Yeah, binary numbers used for coding as well. So if you want to, for example, label, maybe I ask you this question. For example, the number of students in this class are 75 or 6, almost. How many bits I can consider to label every person one unique binary number? How many bits we need to consider? So we are 76 students. How many bits I need to find this N1? Sorry, N1, N. We know M is 2. We want to find N. How we find N? Do it. I want to see who can find first. So we are 76 students. So it means we know this number of outcomes is 76. Okay? How we can find N? Yes. Yes, that's correct. But log, we need to seal it up. We need to seal it up. Okay, so exactly, the answer is log. Maybe I clean this part and right here. But we need to seal it. Seal it means find numbers that is bigger than that. Seal it up. Normalize it, kind of. Okay. So what we said n power n, 2 power n is equal to 76. Okay. So n is log of 76, but we need to seal this up. Okay? So if we seal it up, because if we use 6-bit, 6-bit gonna be 64, I think. It's not enough. We need to use 7, but 7 is 128. It doesn't matter. So this is gonna be 7. Did you get my point? So we need 7 bits, even though some part of that is not still get used, but still we need to consider more numbers because that's why we seal this up. This part coming from that. It means if become, for example, 6 point something, we consider 7. Question? This is called coding as well. You're just a kind of coding as well. Because it was related, so I just mentioned that as well. Okay, good. That's counting with replacement. Let's make it a little complex. So that's just considering that. Oh, this is another example. We have letters A to Z. In English, 26 letters. We have 26 letters. And consider we want to find how many words with 4 letters we're going to have. So, a word with 4 letters. Okay? So the number of outcomes gonna be, because each of these can be 26 and we have 4, so we need to power 4. Okay, that was another example. Okay, so let's do one eye clicker. Right, it's still, I need to define that first. Try to solve it, but still, you can go there. I need to. Good. Fix it. Yeah, B is correct because so the point is we are asking, we have 52 cards, and we have 4 queens. We are taking 7 cards from this, but we replace it back. So it's always going to be 52. But what we are asking, what is the probability that no queen are drawn? Because we have 4 queens, the probability of not queen drawn is 48 over 52. And because this repetition is independent, we are doing 7 times, we are powering this by 7. So the B is the correct answer. Okay. Now let's make it a little tricky. How we make it tricky? Let's consider fixed counts. Like, for example, you have a jar of multiple marble, and you want to see, you are taking 10 out of this. For example, here is, we don't care, 100 inside, and we are taking 10 out. We want to see the number of cases that from these 10, 2 of them be red. It makes it a little complex. So the general case is that the number of observation sequence for n sub-experiments, so we take n out, let n be, for example, 5. So we take n out. Okay, and we want n1 is, for example, red. We want 2 red, and n2, n0, sorry. Oh, we can n0, 2, n1, for example, 3 white. Okay, 2 red, 3 white. Oh, what happened? 2 red, 3 white. Okay. So what is the number of outcome? The number of outcome is combination. But in this case, because they are filling each other, it means n1 is n minus n0. This is kind of binomial. We call it binomial because we just have 2 outcomes, red or white. So in this case is from n. If you want 2 red, for example, n is n0. So 2 from 5. Okay. So if you remember that, it was 5 factorial, 5 minus 2 factorial, and 2 factorial. Okay. So this is a binomial. Later on, we're going to see that we have a distribution regarding to this. It's called binomial distribution. But I'm not going to talk about that distribution because first I need to explain what is distribution means next class. But this is just counting. We want to see how many cases we can have. If we take 10 out, 2 of them is red. If 2 of them is red, means the rest are white, of course. Okay, so how we can count it using this combination, and it's called binomial. Because why is binomial? Because we have just two choices. If we have more, we call it multinomial. If we have 3 colors, for example, 4 colors. Okay, so the general formula is coming from that. Any question about this? I'm just going to remove this to show the cleaner version. It's all the same. Yeah. No question. Okay. So, clean this up. So we want to see how many sequences have exactly this number of outcomes. So that's why it's called fixed count. We know some information. We have some prior information. Those fixed counts, we know that. We want to see if 2 of them is red, now how many outcome we can have. So this is called fixed count sequence, or binomial or multinomial that we can see. So the formula coming from combination, because n is actually n0 plus n1, we can find, we don't need to know the rest. If, for example, give us n0 is 2, the number of red, so we can find number of white, n minus 2. That is, because n was 5, 5 minus 2 is 3. That example. N was 5. Okay? So this is how we are counting that. Let's have, this is another example. So we are doing 5 trials, and 3 of them be 1. Imagine there is just 0 and 1. Okay, if it's 0 and 1, it's like red and white. So the number of outcomes is going to be a combination of 3 from 5. Okay, that's not difficult because it's just 2 cases, 0 and 1. If become more than 2 cases, binomial become multinomial. That is in this category. Okay. Imagine you have a jar of marbles. Some of them are red. Some of them are green. Some of them are blue. Okay, and we take 5 out. We take 5 out, okay? And what we want to find, number of outcome for 2 red, 2 green, 1 blue. If we add them up, it needs to be 5, of course. In this case, we have more than 2 choices. We have 3 here. So we want to see what is number of outcome in this case. We want to find this one. What is this? With this prior information, we take that much out. What is the number of outcome if 2 of them be red, 2 of them be green, and 1 be blue? Let example, like for example, red, green, red, green, green, blue. This is one of them. You need to find how many of these cases we can have. That's the number of outcome, of course. So this is coming from actually multinomial formula that is like binomial. From n, you have n0, n1, n2, and m, for example. and this is to n factorial, and 0 factorial, and 1 factorial, and 2 factorial, and so forth. So it is just like that. Let I clean this up, show you the better formula for that. It's like that. Can we get binomial from this? Yes. If we consider we just have n0 and n1, we can get binomial out of this, because binomial is n, for example, n0 is n factorial, n 0 factorial, n minus n0 factorial. So this is exactly similar to the 2 case, because this is n1. Okay? So this is similar to, say, n0, n1, n factorial, n0 factorial, and 1 factorial. That's it. It's similar. N1, because we had just 2 cases, n1 is n minus n0. Okay, that's called multinomial. An example was like that. Another example here, we have 10 students. What about we have 2A, 3Bs, 3C, and 2F. Some of these need to be 10. We want to see how many situations can happen, how many outcomes we're going to have. If we select 10 students, 2 of them have A, for example, 3 of them B, and 3 of C, and 2 F. So it's going to come from 10 multinomial distribution, but we don't care about distribution part now. Just count outcomes, number of outcomes, 2, 3, 3, 3. Some need to be 10, remember? It's going to be 10 factorial, 2 factorial, another 3 factorial, and 2 factorial. If you compute this one, it's going to be the number of outcome. This one. Okay, you don't need to compute this. All right. Any question about that? That was the hardest part. Yes.
On the marbles, are we assuming that there's the same amount of green?
Yes. We consider all the greens are exactly the same. That's a good point, yeah.
How would you find it
if they were different? If they were different, we are acting like cards. They are not same colors. They don't have a category for that. Yes, this is gonna be similar to cards. In this part that we are talking, that was a very good question. You got that. We have some similarities between these trials, and we categorize them in a new thing. You know, we give some new information about that. If we consider these marbles have numbers for them, they are not similar colors anymore. They are different. Like the cards that we have, for example, queens, but different queens. You know, something like that. But we can make this so complex. Don't need to think too much about it. We're not going to go that complex about it, because you don't need that. And if you need that, you can go find it in this way. You don't need to memorize all of these complex things. I just mentioned this because you have in your assignment, you have one question regarding to that. But we're not going to see that in later. That's the last things that you're going to see about it because it can be complex. So you know, I even didn't explain another case for you guys. We have last class we talked about without replacement when we actually consider order matters or order not matters. But right now, we just talked about replacement when order matters. You didn't ask me, oh, what about if the order is not matters? That's something that is not going to happen. But I'm just going to tell you something. So, replacement order does not matters. Okay, I'm just going to give you one example. I just had something. What was it? Oh, yeah. The example of ice cream. When you go buy ice cream, most of the time, ask you, for example, they have multiple flavor. So imagine we have 3 flavors. This is a good example. 3 flavor, like vanilla, like chocolate, for example, and the strawberry. Yes, strawberry. Okay, so we have 3 flavor: vanilla, chocolate, and strawberry. So we have 3 different flavors, okay? But you want to choose, if I ask you how many scoops you want, say 2, for example. You want 2 scoops. One, for example, vanilla, 1 chocolate, okay? But you can choose 2 chocolates or 2 vanilla, okay? So what that means replacements allowed. You can choose 2 vanilla. So replacement allowed. Order doesn't matter. Doesn't matter if it's are like that or the other side. They're all same. This is another case. So it makes it a little more a challenge because you need to eliminate some choices. Like in this case, vanilla chocolate is equal to chocolate vanilla. Okay, so replacement, we have replacement. So this is an example, good example, like write it up. Okay. So we have replacement because we can have 2 vanilla, we can have 2 chocolate, we can have 2 strawberries. Like those USBs that you can connect to similar things, device to those. And in that example, order was matters. If you're connecting, for example, printer to like a first USB, it's different than second USB. So that matters. But here doesn't matter. Doesn't matter is vanilla first or chocolate first. Doesn't matter. It's equal. So what's going to happen? In that case, if you remember, we considered combination. Okay? Here we also need to get combination, but if we consider like K, for example, okay. Here we also have combination, but we kind of adding extra cases. We are not removing because okay. Oh no, we are removing again. We are removing, but in this case, the formula is gonna be n plus k minus 1 k. The permutation gonna be like that. I just wanted to mention some example of like that. If you write it up, like the cases that you can have, in this case, n is 3. So you have 3 flavor, and k is 2. And if you find this formula, it's gonna be 3 plus 2, 5 minus 1, 4. 2 is gonna be 4 multiplied 3. 2, 2, 4 gonna go, and it's gonna be 6. You're just gonna have 6 outcomes. The number of outcomes is gonna be 6. You can see that, for example, vanilla, chocolate, strawberry, vanilla chocolate, strawberry chocolate, one more, vanilla, strawberry. Yes, that's it. No more. As you can see, it shrinks to 6. And this formula actually coming from that. Okay, but just consider this example. We're not going to go more deeper into complex. Okay. Let's clean this up. Example. So let's go to binary because we are computer or, I don't know, electrical engineer, and we need to work with binary numbers a lot. So consider we have 4 binary numbers. 4-bit numbers, 4-bit numbers, and each one 0 and 1. So what is the question? Okay, the question is how many different code we can make with these 4 binary numbers. Of course, each of these can be 2, 0 and 1. So the number of outcome is going to be 2 over 4. It's going to be 16. Okay? Easy. Second question. How many codes have exactly 2 zeros? Okay, that's an easy one. So from 4, 2 of them are 0. So we know this is combination. From 4, 2 of them. So it's going to be factorial, 6. Yes. Why? Because like it's going to be 0, 0, for example, 1, 1. It's going to be 0, 1, 0, 1. It's going to be 0, 1, 1, 0, because it's 6, I can write them all up. 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0. That's it. It's 6. Okay, that wasn't hard. We knew that. Now let's make it a little more complex. What about if we want to have how many code begin with 0? Okay, so if we begin with 0, this part is changing. We don't care about one of them. One of them is always 0. So the number of k is going to be 2 power 3 to the 5. Because this is 0. Just we are changing these 3 bits. And these 3 bits can have 2 power 3 cases, 8 cases. So that's the answer. Any question? Okay. So let's clean this up. The answers more cleaner version here. Okay, that part done. We're done with counting now, at least in this part. We're going to move to a new topic, a little new, that is called actually reliability. We want to see how we can design a system more reliable. Of course, in probabilistic points of view, how we can make a system reliable. You had experience in this case a lot for sure, especially when you are working with internet, with sometimes some stuff happening. And if, for example, Google get problem with Google, they need to design it a proper way. If, for example, the server is down, like a billion people, maybe people working at the same time, they're not going to feel it if one of the servers is down. So the system needs to be kind of fault tolerance, need to tolerate fault. We call this kind of system fault tolerance. And this is coming from reliability points of view, how we can make a system reliable. In these cases, in networks and servers, we always have redundancy servers. They have multiple servers, and they have some like load balancing system. If one part is, not working, the other part's gonna replace that. So this parallel work makes system fault tolerance. We're gonna see in terms of probability. So in this case, we have 2 different type of components. That these components are independent. They're working independently. They can connect serial or parallel, or combination of serial or parallel. Like, for example, you can put a server like this, another one like this. In this case, it's serial. If one of them break, the system gonna break. But if you make that parallel, and you're independent, if one of them break, if one of them get, failure or whatever happened to that, the still system can work. This kind of system is actually more tolerating a fault. We call them fault tolerance. So we're going to talk about this. Assumption that we need to have is that they need to be independent. These modules, these components need to be independent. If the probability of success be P, probability of failure is 1 minus P, okay? And how we can make the system to actually be tolerate. First, in serial case. The serial case is when we put these components in a serial case. What is the probability? How we can consider probability? So in serial case, like this picture, if we consider probability of success for one of them is P, probability of success for all of them is P of each one need to be success. like P of one is P, for example. The overall is P, P1, P2, like n times. Because they are independent. So it's going to be P power n. So that's the probability of being success for a serial system. Because they are serial, if one of them get, problem, the system gonna get problem. Okay, that was for serial system. What about parallel? In parallel case is different. If we consider, for example, again, same things, these components are independent. This system can be used for fault tolerance systems. Fault tolerance systems, like, for example, backup servers, computers that have a specific, like a spacecraft computer that need to tolerate failure. Redundant servers or redundant sensors also can be used if you want to have precise, system. You need to have multiple sensors that cover each other. If one of them has problem, the other one work. In this case, probability of failure, we're considering here probability of failure in this case. Probability of failure for each one is 1 minus p. Probability of failure for all the system is 1 minus p power n. And probability of success is 1 minus that. Probability of success for all the system is 1 minus probability of failure. Probability of success is 1 minus probability of failure. Okay? So that's simple, that's not complex. What about we combine them together? That's also the same thing. If we combine them together, we're going to have one example for combination. Like imagine you have, this example is 2, but I draw 3, that's fine. We have 2 subsystems in parallel, okay? So we just have 2 of these. We have 2 subsystems in parallel, and each one has 2 components, okay? Subsystem 1, W1 and W2, and W3 and W4. Like this is W1, W2, W3, and W4. Okay? Okay, so what we want to find, probability of success. What is probability of success? This is what we want to find. Okay, first, what we have, we know that these systems are independent and probability of success for each one is 0.9. 90% they work good. Each one. We have this information. What we want to find probability of success for all the systems. So the probability of success for all the system, probability of success for the serial part is P2, based off what we mentioned. And probability of the parallel case, we can find probability of failure probability 1 minus 0.81 over 2, and then probability of success is 1 minus this, because I don't have time, I just write this up. So what we did, we find the probability of serial case, and then the parallel case, we found the probability of failure for each serial. And then we have probability of failure for all the system because they are complement each other, failure and success. So probability of success is 1 minus probability of failure. So it's coming from that. Any question about it? This wasn't difficult. So, but if you have any question, let me know. Okay, so we have the new assignment. And also, we also have survey for the class. I want you to mention what you like and what you don't like and what you want to change. Just write it up. It's going to be helpful for everybody. Okay, try to do that. Anything else? Yes. First exam? First exam is before this break that you're gonna have. It's not break, it's winter. It's before that. Yes. It's gonna be probably.
How does this guy not know what it is?
Is it next week?
It'll be next
Yeah.
Tuesday.
Okay.
Bro doesn't even know what's going on.
I'm gonna let you. Thanks for asking.
I don't know how this can. Oh, we're gonna have one before this.
You mean next week? Yes.
We just got.
So excited to have Tampa. I can't remember.